acceleration varies with displacement. Now the last part is how velocity varies with displacement. So over here I need to change the sine term to a cosine term. How do I do that? Via this trigonometric relationship. If I have sine square A plus cosine square A equals 1. This is a trigonometric identity that the student should be familiar with. Therefore, sine of A will be equal to plus minus 1 minus cosine square A. Okay? Whole under. So I can use that there. I get velocity equals plus minus omega x naught whole under root 1 minus cosine square omega t. I'll just take the x naught term inside the under root sign and I get x naught squared cosine square omega t. Okay, this here, as we can recognize, is nothing but x squared. So x naught squared minus x squared. So this is how velocity varies with x. This in higher mathematics, students might learn that this is actually the graphical function of an ellipse. So they don't need to know that, but you can simply tell them that this relationship is an ellipse. It will be a circle when omega takes on the value of 1. So we can just see how this will vary. Okay, roughly an ellipse varying between x naught and minus x naught. You can tell them how this shows that the velocity is 0 at the end points and maximum at the equilibrium point. Over here, the value would be omega x naught, and here will be minus omega x naught. Okay, so this is how velocity varies with displacement. So those are the 5 curves that will help the student identify how or rather understand how a simple harmonic motion works. You may or may not choose to go into so much detail. I like to do this so that the student understands it. Now, in an exam situation, rather than memorizing formulae, the students simply need to firstly identify at what point was the timer started. Was it started at the equilibrium point or at the end point? So at the end point, like you just derived, your displacement takes on a cosine curve. You differentiate that once, you get the velocity curve, and differentiate that another time, and you get the acceleration curve or the acceleration equation. Now let's say the timer had started when we were at the equilibrium position and moving towards the positive. That would be a sinusoidal function. Again, just differentiate this once and you will get the function for, you'll get the equation for velocity. Differentiate this another time and you will get the equation for acceleration. Notice that this will again yield minus omega squared x for the acceleration, and for the velocity we will always have that same relationship with displacement, plus minus omega whole under root x naught squared minus x squared. Okay, so the students should be able to then derive without actually memorizing the formula. On the spot they can know which one of the formulas or which one of these sets they need to use to solve a particular simple harmonic motion. Yeah, from here on we'll move on to energy in simple harmonic motions. Okay, so 4.2 is discussing the energy changes in simple harmonic motions. Okay, just now one of the equations that we came to was how the velocity in a simple harmonic motion varies with the displacement. Okay, we'll be using this for energy changes. Okay, from the graphs that we saw, we know that the velocity at the end points, or the points where the object transcribes the maximum displacement is 0, right? Whereas at the equilibrium position, the velocity is maximum. Okay, which means that the kinetic energy Ek at the end points is 0, whereas at the equilibrium position, kinetic energy is maximum. Okay. Subsequently, by conservation of energy, the total energy, of course, in a simple harmonic motion is conserved. It's not lost, as we said that the oscillations are not damped. So the total energy remains constant. Okay, and since all the total energy is converted to kinetic energy at the equilibrium position, the potential energy or the spring potential energy, okay, the elastic potential energy is 0 at the equilibrium position, and all of the kinetic energy gets converted to the elastic potential energy of the spring at the maximum positions, maximum displacements. Okay. Now to find the value, let's take for example this point here, Ek max. Okay. Firstly, the addition of all of these is equal to the total energy. Okay. Now, at the equilibrium position, to calculate the maximum kinetic energy, we just have to substitute the displacement as 0 at that point, and as we know, kinetic energy is given by half mv squared, so that will be half m plus minus omega x naught squared minus 0 squared, right? That is simply half m omega squared x naught squared. Okay. Now we know that at the equilibrium position, this is the maximum kinetic energy, which is also equal to the total energy. Okay. So therefore, the total energy is given by this this function over here. Now, if we have to calculate the kinetic energy at any general point x, we have to follow the same method. At any point or any displacement, the kinetic energy will be given by half mv squared, which is equal to half m plus minus omega x naught squared minus x squared whole squared. Okay, that is equal to half m omega squared x naught squared minus x squared. Okay, so this is the kinetic energy at any point in the oscillation. Okay. Now to get the potential energy at any point, we simply have to see that the potential energy equals the total energy minus the kinetic energy, which is equal to this term here, half m omega square x naught square minus half m omega square x naught square minus x square. Okay, you see that this term is the same as this term, so they get cancelled out, and we are left with half m omega square x square. Okay, so that's the potential energy at any point. Okay, so we have the total energy, kinetic energy, and the potential energy. Now, if we had to describe these on a graph, we can do so. graph of how energy varies with displacement. Okay, so firstly, at the maximum displacement x naught and minus x naught, we know that the kinetic energy is 0, and at the equilibrium point the kinetic energy is maximum, which is going to be equal to the total energy, half m omega square x naught square. Okay, now you can see that the kinetic energy varies with the displacement as a quadratic function. So the curve would be a parabolic curve. Okay, so that's how the kinetic energy varies. Now for the potential energy, it would be the opposite of that. At the maximum position here, we have maximum potential energy, okay, which is also equal to half m omega square x naught, which is the total energy, and at the equilibrium position we have the potential energy equal to 0. Again, it's you can see that it is a quadratic curve, so it would be like that. At any one point, if you add up the potential energy and the kinetic energy, it should give the total energy, which is described by this line here, which is half m omega square x naught square. Okay, so that's energy in a simple harmonic motion, and you should be able to ask the student to solve a few problems, both graphically and by calculation, using the energy in SHM. So that's 4.2.